share the screen and then we can start now. So I can start. Sorry for a little bit delay. I hope your sound is safe. And let's get ready for the class. So let's very quickly review what we have done. Because of the time constraint, so I make the review shorter than usual because of the time constraint we have. So descriptive statistics. So what we are doing here is trying to say if you have given data, we try to do some analysis. Okay. Sometimes people call it exploratory data analysis. So try to explore the data because the first time you get the data, try to see where the data problem and try to see what funny thing you can see, right? Because the data also oftentimes issue. So you want to look at the mean, median, mode, and variance to see you get the right data, right? Because somehow you might get some idea what data should be and from other experience and from your domain knowledge. Okay. So we mentioned statistics actually divided in two parts, right? One is descriptive, one is inferential statistics, and the first half of the class we focus on the visual and numerical representation and probability, and then so on. We have the estimation for the subsequent part, right? We try to generalize the data we learn from the data to see if it applies for the population. So much bigger aspect. And we understand data at different types, right? Because different types and you would require different tools. And just to remind you that most of the technique we learn is applied on numerical data, particularly continuous one. The reason is because it's most easiest. And suppose you consider data with discrete, then things become well different. We need to make some more assumption and make some more tools, and same as nominal and ordinal. We actually need the easier data actually require a more advanced tools. So you can and in application most of the time we handle the continuous data, so shouldn't be an issue. But if you try to generalize it to a more different type of data, then you have to be careful, right? Just to remind you that say ordinal data, adding and subtracting and multiplication doesn't mean a lot, right? So that's why when we calculate mean, even median, right? So there's some issue there, right? Because median you involve taking average of the two if your observation is even number, right? So there's some issue here, but nevertheless, we just don't talk too much about distinction, but rather we just keep it as it is, right? So just remind you to keep remember that what we're doing is focus on numerical continuous data, okay? And the reason why it's easiest, and then others actually require more tools, more different tools to do it, okay? And again, we just use this slide to talk about visual or graphical representation of data. And just to remind you that although I just spent one slide, indeed, this is the single most important thing when you present your data to your boss, as the first impression sticks. And same for your projects, right? So I expect, this is arts rather than science problem, right? It's just how you present your thing. You should be able to do it and you learn it. Since your primary school, right? You how to present your stuff, how to make things look nicely, how to use color, how to use font size, what to emphasize. And this is something you should be able to tell me. There's many things, a lot of things to be done here, but because of the sake of time, we have to focus on a more technical aspect, right? Of course, the graphical thing is like the first round approach, but you need to support it with more detail and technical support for that, right? Same as a report, right? Expect to present the executive summary, but all your finding must be supported by more rigorous approach, okay? And last time we covered half of it, right? So there are three ways to represent data, right? Central tendency, dispersion, and shape. And we fully discussed the mean, median, mode, and dispersion. I think we start with the range, and we stop somewhere in the interquartile range. And then today we'll finish dispersion and shape. If we have time, hopefully we finish all the theory, and then we can talk about Excel next class. If we can't cover this class, okay? So let's very briefly review what's mean, median, mode very quickly, because I think you know what are they. I mean it's just sum of them divided by total number of them. And again, I need to remind you that for this to make sense, it has to be numerical data, right? Because otherwise, because the definition of this mean is middle in the distance. I mean, for this to make sense, the distance has to make sense, right? Distance doesn't make sense, and this doesn't make sense. Is that clear? Okay. So just to remind you, this graph, I think this is the most. That's why you say graph is good, right? I think this is a good representation of the mean in your idea, right? Because it simply means the distance to the left, which represented by the red color, should be equal to the sum of the blue distance, right? So it's we adjust location of mean until the two area equals, right? That is the meaning, right? So that's the center of the data. And just try to recall, this mean actually would be affected by outlier, or what we call extreme values. And whether extreme value is a feature of data or your data problem, it depends. But if you want to focus on mean, sometimes you would consider handling data a little bit, trimming or winsorizing, but we're not going to talk to detail about those. And the second is median, right? And the median is the middle of data. And if odd, then it's exactly the middle exists. Then the even, we will take average of the middle two. And again, the middle two, it will make sense if actually the middle two can be added, right? If you can't add, then probably the right way is not to add from the average, but instead telling people what are those two numbers, right? But of course, to make our life easier, just telling you the number, right? And especially when the middle two is actually very different, then actually the median is not really a right rate, right? With the median is like 1 is 3, 1 is 10, then probably it's not good, right? If 3 and 4, but probably report 3.5 is good, right? So if 1 is 5, 1 is 100, then probably within the middle is not really a good way. But nevertheless, we just follow the standard way, right? Just average. And when data is large, then it's not a problem. But when you imagine the two middles are very different, then you should be very careful about that part. And because it's exactly middle, so it doesn't affected by the outliers or extreme values. So that means that the data quality for median is much less than the mean, right? Because the quality is bad for the mean, then everything will be screwed up. Okay. And lastly, the mode. Just want to emphasize the mode you learn may be different from what you learn in the high school or elementary school, because with the most frequent value approach, that means that if everyone appear once, we still call all of them a mode, right? And compared to median and mean, median and mean only give you one number. Mode can give you more than one. So, but the good thing about mode is that we don't do any operations, right? So this mode apply to anything data you think that is we use, right? Nominal, categorical, right? Discrete also works very well. Okay, so that is the three things. Okay, last is the range. Okay, and interquartile range we covered last time, and they are measuring dispersion. And dispersion is looking at how spread data is. And remember why I want to look at the spread of dispersal data is because this gives you the idea how accurate our central tendency measure are, right? It just gives us how good are the mean, median, and mode they are, right? If you expect a larger range, then the mean is not very representative. Same idea as mode, median, and so on. Okay. And just to remind you what's the range, right? Range is the biggest minus smallest, right? If you order data with xn minus x1 from ascending order, right, from smallest to largest, and easily you can see that it's subject to outlier, right? If the outlier, then your range will be very large, right? So either you want to windsorize it, right, or you want to trim it, right, or you want to consider another one we call quartile, IQR quartile, right? Quartiles, remember quart is 4, tiles is means parts, right? And then you divide it 4 equal parts, right? And by definition, it's very simple. It's like 1/2 of n plus 1, right? 1/4 and 1/4. But what do you mean by 1/4 is not very clear, right? It's say if like this number is like 0.5, right? We divide by 4, right? It's 0.5. Let's say, suppose it's 7.5, right? There's an average of 7 and 8. That's no problem, right? And if exactly integer, that's not a problem, right? 0.5, just like what you do in the median, right? The average of the two, right? But what happened? You divide by 4, right? You learn from the primary school, right? What kind of number you can get you divided by 4, right? For decimals, either you're 0.5 or 0.25 or 0.75, right? It's either 1/4, 1/2, or 3/4, right? Or you have a whole number, you don't have fraction, right? So how can you able to say what happened when we have the number say 8.25, say, right? The number is between 8 and 9, right? The data, right? What with 8.25, how do you do that, right? So there are many ways to figure out that. Either you just solve the problem, you just forget about this, right? You just remember what we do is like find two median, and then you ignore this problem, right? Or you actually do the interpolation. That's all we do with method 3 very soon. But let me remind you how you can do this interquartile range, right? So just to remind you that the range is the largest minus smallest, right? Interquartile range will be the median of the first half minus the median of the second half, right? So just to remind you, the idea is the following. And there are 3 methods that I think that if you try to use it in practice, there are many ways. 1 and 3, I think you can still find out, but you can't do it in Excel. Okay, so that's why I had to teach number 3, because this is correspond to Excel or R or Python. Okay, so let me repeat what you learned 1 and 2. 1 and 2 is what you learn in the primary school or high school. And the method you do is very simple. You just look at the median of data, okay? And the median will help you to cut the data in half, okay? And then you find median for both. And method 1 will include the median and data, and method 2 will not. So that's the difference, okay? So quickly, we just go over again. Look at the data here, okay? 1, 2, 3, 4, 5. The median is 3, right? Why median is 3? Median is just n plus 1 over 2, right? N is 5, 5 plus 1 is 6, 6 over 2 is 3, okay? The third data is 3, okay? And method 1 tells us that we will include the median into our division, okay? So that's why the first half is including 3, okay? So 3 numbers, the median is exactly middle, which is 2. So Q1 is 2, okay? And the other way around is looking at the second half. Remember method 1 will include the median into the division, okay? So 3, 4, 5, the median is exactly the middle one, which is 4. So that's why the IQR is just 4, okay? You can easily contrast it with method 2, which we covered last time as well. Method 2 will not take the median into the data. So that's why the difference is whether you have 3 here, right? Because 3 is exactly the data. And method 2 will say we will not taking this 3. So 1 and 2, okay? And 1 and 2, 2 numbers. The median will be just average of the 2, right? Because median is just 1.5. Why? Because n is 2, n plus 1 is 3, 3 over 2 is 1.5. 1.5 is halfway between 1 and 2, which is 1 and 1.5, right? And similarly, we have a 4.5 here, right? Because 4 and 5, right? Because don't include 3. So the median is 4.5. So the IQR is just the difference between the 2. So that's 3. Okay. So now let us don't forget about the method 2. Okay. They are what you learn in the high school or primary school. Okay. So what we're trying to do is method 3, which is a consistent way to do things. Okay. And how we do that is trying to start from the first principle. Okay. How we define this. This is the definition. We'll exactly use this definition. Okay. So how can we reinterpret this? Okay. Now, remember, this is how we do it, right? What we do is halfway between 2 numbers, right? Suppose this Q2, right, n plus 1 over 2 is like 4.5, like 4.5. Then what you're going to do is the number, 4th number, and the 5th number, average of them, right? But you can interpret in this way: is you start from the 4th, plus halfway of the difference, right? So let me say it out. So this is, let me see if I can use the pen. If not, then hopefully we can, but who knows? Things can be different. So x4, x5, okay? So what we are doing, if say the number is like 4.5, right? This is 4.5, right? Suppose like n is 8, right? Then this guy 4.5, right? So then what you're going to do, right? What you say is 4 plus 5 divided by 2, right? This is, right? That's how you do is you calculate median, right? So, but you can imagine this is same as what talking is 4 plus halfway of 5 minus 4, right? So you can start from the smallest number plus the half of this distance. Is that clear? Because they're the same thing. Can you see that they're the same? Average of the two is same as you start from the smallest number plus halfway the distance. Is that clear? Is that okay for this one? Okay. That actually, when you learn math, if you learn M1 or M2 or the math, then you learn this is what we call interpolation, right? Just halfway, right? So this would apply even this not half, right? Suppose what we have is, so suppose n is 8, right? Make it easier. N is 8, and n plus 1 is 9, right? And 9 divided by 4 is what? 9 divided by 4, 4, 8, right? 25, right? 2.25. So how can we do, which one number to take, right? Is x2 and x3, but what we want is x.2.25, right? How can we figure this out? What's this number? Okay. So it's very simple. The formula is the following. It's just x2 plus 0.25, or if you want, it's a quarter, times the distance between x3 and x2. Okay. Where's 2 and quarter? Very simple. Where's 2 and quarter? It's just starting from x2, okay? A quarter way of the distance between the two. Is that clear? Right? So suppose I have, again, 9 plus 1. So 8 plus 1 is 9, right? 3 times 4 times 9, right? It's 27 over 4. Right? Okay. It's 6.75, right? So what we have x6 and x7, right? But we want is x.75, so we'll do x6 plus 0.75 plus x7 minus x6, right? You start from 6, right? And some third quarter distance, right? So that is actually, in math, it's called linear interpolation, right? So probably you would, I can convince you this is the right formula by using this. This is the, what we're trying to convince you, this is a similar triangle. Okay. And the idea is behind this. Okay. What you have is, this is an integer, right? K plus 1 plus 2, right? And there's somewhere in the middle, right? Okay. So what we are going to do is look at what, say this is, say the previous example, right? This is say n is 8, right? What we have this example, n is 8, right? And suppose p is the, right, one quarter, right? And this is 9 over, this is, right? Then this is like 9 over 4, right? This is 2.25, right? And it is, in this case, this is between 2 and 3, right? x3 and x2, right? And x3 and x2 is this number, okay? And what we're going to do is use what we call interpolation, right? This alpha is 1/4, or 0.25, okay? And this is the distance between the two, right? This distance. And you want to calculate how much you should go, right? So it's by similar triangle, you divide this, okay, to, that is the formula here, right? Similar triangle implies alpha over 1. So it's this over this will be same as this over this, right? This is what similar triangle is, right? If you still remember, you learn in the geometry, all right? And you just multiply, use cross multiplication and move the xk. This is the formula, right? This is exactly the formula we mentioned, okay? So you don't need to worry about this because we will exactly implement this in the example, then you will see what we're going to do, okay? So don't worry. We just implement this, it will be very simple. The formula look crazy. We need to look crazy because when you apply it in the software, then have to be right in this way, okay? Of course, if I give the number, you can easily do it, okay? So let's do it, and then you will not be scared, okay? The only scare thing is because you don't know what to do, okay? But I show you, then it'll be very simple. It's so simple that you think is what I'm doing is like crazy, but once you look at it, it's very simple. So here I have data is n is 5, right? N is 5, okay? N plus 1 is what? 6, okay? So it means that the Q1, okay, is indeed, right? The 6 plus 1 is 6 over 4 data, right? It's actually what? 6 over 4 is 1.5, right? Or when you write is x 1.5, right? So is that clear? It's between the first number and second number, halfway, right? So if you follow our formula, will be just x1 plus halfway of x2 minus x1, right? So it's because 1.5. Is that clear? So x1 in our example, which is just 1, right? And 0.5 is exactly, x2 is just 2 minus 1. So it's just 1.5 here. Is that clear what we're doing? Don't worry, I'll give you more example, then you'll be less intimidating. I mean, once you work it out, the answer then should be easy, okay? And don't worry, as I said, this one, you do Excel, you give you the answer directly. I just give you the reason why you get it, okay? You don't have to work on it. I mean, of course, for example, probably you need to know, but I mean, otherwise, that would be how it's being calculated, right? What is Q3 here? Q3 means this is 3 over 4 times 6 data, right? So you simplify, right? 2, 3 is now over 4. Okay. So that is actually, am I right? Yeah. .2. So it's 4.5 data. Okay. So which is x 4.5 we to find. That is very simple, right? It's just x4 plus halfway of x5 minus x4. Is that clear? This is the answer, right? In this case, because x4 is just 4, right? That make our life easy, right? And x5 is just 5 minus 4, right? So that's why it's 4.5. Is that clear how we get it? But of course, the notation I use there is just trying to convince you that it's a systematic way to do it, but the same idea. Right? Because the formula here, what we said is this is getting the integer, right? Same as what we do, right? So integer, just because the integer that less than this number, right? And take a difference. The same thing, the same formula. Don't worry, I will go to another example, then you see. Okay. Is that okay for this one? So don't worry. If you don't understand, I'll give you more examples. So don't worry. Don't worry about that. So this one, 1, 2, 3, 4, 5, 6. I think it's good to go to a whiteboard, right? So for that one. So the data, what we have is the following, right? So data, what we have is 1, 2, 3, 4, 5, 6, right? So n is 6. Is that clear? So n plus 1 is 7, okay? So Q1 will be, remember the formula is n plus 1 over 4th data, right? N plus 1 over 4 is 7 over 4th. Is what? If you do it, is 1/3/4, right? And or you want is 1.75, right? I think I'm right? Yeah, I think that should be right. Okay. So how are you going to do it? 1.75 is just basically you start from 1.75, right? What you're going to do is will be x1, right, plus 0.75 x2 minus x1. Is that clear? Because 0.75, right, is like you get 75 3/4 of distance of that one, right? So x1 is 1 in this case because we make life very easy for us. 2 minus 1, right? So it's 1.75. Is that clear how we handle that? Okay. So same idea. Don't worry. You only need to know how to calculate this, okay? In practice, I mean, you have Excel, you do it, right? So don't worry about that. Q3, right, is 3/4 times n plus 1 data, right? So it's 3/4 times 7, right? And this is 21/4, right? And that is actually what the data 5 to 5, right? Okay, or if you don't want so quick, then it's right 5 and 1/4. 1/4 is 0.25, right? And that means it's 5.25, right? And how we do? You start from the 5th, right? Take the integer, right? And will be a quarter between 6 and 5, right? So it's just 5 plus 0.25 of 6 minus 5, right? So it's 5.25, okay? So it'd be same as your slide. Is that clear what we're doing? Okay? So why I do that? Because Excel gives you this one. So you understand why Excel gives you this one. Otherwise, why we bother, right? And the reason why this is good because it's consistent. We just linear approximation, right? Linear interpolation on that. So this is the standard way we do things. So that's why I keep it. Okay? Is there a question? Hey, hi. Is there a question? If no question, then go back. Is there a question for this one? I think this is the most difficult part for this one. Okay, that's how you get that two number there. Okay, but this formula is the same, right? Because 5.25, right? Just fifth and a quarter of 6 to 5. Same we have done. Okay. Now, this is a box plot, right? The box plot actually is very helpful for you to draw the quantiles and the mean and median and see the range in the quantile range, right? So this is the graph that usually you should present when you try to compare data, right? You see which one is more spread out, which one is concentrated. It's a good graph. Okay, I just put it there for it to do it. Is there any question for the IQR? Is that okay? Later you will see, Excel function that give you this one. So that's the reason why we cover that. Okay. And the following would be very simple because this is the formula you have learned when you are in high school. So variance by itself is very simple. The definition is just as is said here. The variance is average square distance from mean. Okay. By definition, it means that every data you subtract from the mean, take the square. Okay, average means sum of them divided by n. Right? Just basically add them up divided by n. Okay, this definition. Okay, we will go for example and how you can do it. Okay, but this is the definition. Okay, and you probably ask why we need to take square, right? There are two reasons. First, take squares, you know, is easier in math because if you learn calculus, take square, you can take derivative, it's easy because it's differentiable. It's nice, it's a smooth function. Okay. And the natural one you can imagine in your mind is absolute difference, right? And turn out if you learn calculus, it's non-smooth. Let's say mathematically that is actually more difficult to handle. Square actually is easier to handle if you learn calculus. Okay, the first thing, mathematical convenience. Okay. The second one is variance as a good thing is it actually, you know, square means that the further away, square get bigger, right? So it means that even the data have the same distance, but if somehow some data is further away, the variance is larger. Okay. So it does means that you get some idea of the spread, right? If it is very far away, right, the mean, then I want it to be bigger, because square idea. Okay. And that is definition. That's nothing. Okay. And here I have what we call sample counterpart. We have some adjustment factor here. What we said is instead of dividing it by n, I have n minus 1. Okay. So probably you ask me why I have this one. Okay. First, my answer is Excel. Okay. Will give you this one unless you ask him to explicitly give you this guy. Okay. And probably ask me why we use the below but the above. Right. It's because later when we learn in the 5th topic, okay, we'll learn that the sample one, which n minus 1, is a better measure of what we want to measure. Okay. So that's why we always use this guy. Okay. When we actually apply to data, they call sample variance. This is called population variance. And you will learn it in the 5th class. So no, the 5th topic, topic 5. When we talk about estimation, we talk about why this one is better. The idea is called unbiasedness, is a better estimate. Because when you collect data, when you try to estimate, it's not working, the mic. Yeah. This one is a little bit better. Okay. So we will see if you look at Excel, this is called variance. If you do variance or variance dot X is this guy, and this is the variance P. So you have to explicitly call it in order to do it. But anyway, we'll talk about Excel later. But the reason that I introduced both of them because you see them in Excel, right? And also by default, people when we talk about variance, it's called sample variance. It's n minus 1. Okay. I mean, we will see what they are, but this is the way. Okay. And this is better is because if we want to know the variance in the population, in the big picture, if you collect data, if you try to guess the big picture variance, well, then when you have data, you use the n minus 1 version. Okay, a little bit tricky, right? Because what you want to measure is actually this guy, right? But when you collect data, try to do it, you use n minus 1 version. A little bit convoluted. Okay, your mind has a little bit twist a little bit in order to bang your head to the wall to understand. But you clearly see what happened in the topic 5, and then we'll see why. Okay, but and you can see this is larger, right? N over n minus 1. So because kind of like you collect the idea is intuitively like you collect sample, right? And you just get a small picture. So you kind of underestimate the variance. So it's just a little bit bigger. So I think that is if you want to understand intuitively, that's the idea. So you know to estimate what happened in the big picture, the big variance, you collect something in the small one, then the variance is smaller because you could see some part of it. So it's enlarged a little bit. And when the sample size is very large and it's very big, then actually that these two will be the same, right? Very similar. That's why collecting kind of people would say this is a adjustment for the small sample, right? The sample is large, is the same thing. I hope that I convince you this is something we will explain later. So just take it. And this is the population version, this is sample version. Okay. So I hope that will be fine with you. I mean, as I told you, right, when there's no internet, I saw this, I spent a lot of time going into the library to figure it out. I think I spent a few days in the library looking up different books to figure, okay, this is the answer. So, and I'm now trying to convince you that you have to just bear with it, okay? Take it until fifth topic, then you understand why. Okay. Before we have a break, let me show you the example. Okay, so I know it's time to break, but let's quickly go over the example so that you know how to do calculation. But again, I tell you, variance readily calculate from any software. You just need to know how to calculate. Okay, unless I ask you in the assignment, otherwise it's just you don't really calculate by hand anyway. But you have to understand how it comes. Okay, and it's good. I show you how you do Excel, because this is the way you can calculate if you start from scratch. Okay, this is data. Okay, and later when we do Excel, we'll work it out in this way, right? We'll find average. Okay, and for the Excel function later we'll cover. Maybe not, if not this class, next class is called average. Okay, and average. Okay, and there's no mean function in Excel. Surprisingly, they call average, right? Average of this, then deal with data. Okay, and then you subtract. Here you can see, right? The third column is subtracting the mean, right? Right. 1 minus 3 is 2, -2, right? 2 minus 3, -1, so on and so forth. Is that clear for the third column? And the fourth column is just square of the third column, right? Now, how to calculate the population variance? It's just adding all this one divided by 5, 52. If you divide by 5 minus 1, it's 2.5, right? Because adding up is 10, right? So later we verify, probably work it out in the Excel, either this class or the next class. Is that okay? Any question? I mean, we'll work it out Excel, so don't worry. But I'm just telling you how variance being calculated. Okay. Is there any question before we have a break? If no, then we have 2 minutes more than usual, so we'll resume at 3:32. Okay, I'll go around to see if any question. We just actually talk about it. We just cover everything, but thing I'm going to ask them to go back to there's not actually to be in forward. I think that's all. But if there's no issue with them, it's not even I think after you access to the example, it's posing. Okay, you email your with your school email because I was sending I think that's because I say based on latest version available. Just send me the email to this group emails that get your say allocation. That is often that one is my learning online. Over. Yes, please. Oh, this is the boss part, right? This is the be on that. This is you want to figure out this is true is more relevant. Oh, as I told you, this is yeah, I know. This. So this is you want. This is you. This is you about that's what that's the boss point. That's kind of my part number. I mean, you're asking me why we have this. Why we yeah. Horizontal means nothing. You can basically say this file. Yeah, it's easy to recognize what is what, right? Very good question. If any question in the Zoom, if any question, just leave a message because I really not sure if I can see your question, or you can unmute yourself if you need anything. So let's be back. Some of you asked the project thing, but I guess when the airdrop period is over, I think next week, then we can talk a little bit more about project. But I would probably, as I promised, I mean, I'll put the previous year's work that have been done. Then you can work on those. You can see how it can be done. I mean, so don't worry. I mean, it just basically trying to apply what you learn in the real world. Shouldn't be a big issue. I mean, so the next one is standard variation. So standard deviation. Okay, variance is just to remind you. It's just the distance from the mean and take square, add them up divided by n, right? And you can see the further away the data, right, the more difference, right? Do remind yourself that what is mean? Mean is exactly the middle of the distance, right? So left distance and right distance the same, right? And you square it, right? So that's why you will not add up to 0, right? You square it. Well, the further data you are, right? So just give you some idea again, okay? So suppose a number line, right? And suppose your data, this number, and this number, right? And suppose, right? Make it simple, right? This is 4, 5, and 6, right? And you can easily see the mean is just 5, right? And consider another data, which is 3, 5, and 7, right? The mean is again 5, right? But you can see the green one is more spread out than the red one, right? And you can calculate the distance, right? You square this distance, and square distance is more than the square distance plus this distance, right? So that's why the variance is a measure of the how data is spread out. Even the same mean, you compare, right? It's compared to the mean how away the data from, right? Because remember, the mean is the middle of the data in terms of distance. And you often don't see variance, but instead you see standard deviation. Okay. The reason why is very simple. The reason is being, if you take variance, it's square, right? So in terms of unit, if cm becomes cm square, if inch become inch square, meter become meter square, right? Dollar become dollar square, right? So it's not easy to interpret. What do you mean by square? So that's why we always take square root. Okay, the square root. That means that the same unit. Okay. And later you will see that this standard deviation, we often we call SD. Okay. SD. Okay. S dot D dot. Is very important concepts in statistics. Okay. Usually, later you see what we call the. Let me see if I have data here. Let me see if I have here. Oh, I don't have here. It's probably we will talk about this later. It's what we call the empirical rule, which said most of data will be within 2 to 3 standard deviation of the data. So if I calculate the SD, okay, which is square root of variance, right? Square root, that's very simple. Just most of the data will be within and minus, plus minus 3 SD. Or sometimes 2 SD is sufficient, depend on what kind of thing you're looking at. Okay. So SD is good because it's within the same unit. So you can add and subtract. So basically, look at it. You calculate the mean, look at within 2 SD or 3 SD. Okay. Basically, it's where data is about. If things are beyond 2 SD and 3 SD, that is very rare. Right? That is exactly what, similar to what the government said, right? We said the rain is only once in 300 years. How can they qualify this kind of statement? Exactly that's what it means. Look at the mean, look at SD. You're beyond 3 SD and 4 SD, basically it's just like out of thousands here, billions here, this kind of idea. Okay, of course, what they said is actually they behind have a more complicated model and try to model it like this way, but simplicity is just like if above the mean several SD, basically just like out of hundreds of years. Okay, I hope this convinces you. Again, we have a sample counterpart. Okay, and later we will learn Excel. Then probably this just remind you what is the formula for this guy will be. They call STD. What's it? DX. Is that D? Yeah, something like STD. Yeah, I think that's the case. Okay, so that it will be there. But okay, we'll talk about Excel later. Okay. So next we will be talking about is the coefficient of variation. Okay, so this is nothing new, but just SD over the mean times 100. Okay, this is usually they call it percentage. So you can see there's some reason why we want to divide it by the mean. Okay, why? If you learn math, we just have done why we have variance and SD, right? Is this one has no unit, right? So why is it good? It means that regardless of how you measure it, whether you measure it per thousand, per million, per billion, CV, we get the same thing. And the good thing is you can compare across data set, right? If say you want to say there are more variance in say statistical class than say principal econ class, okay? But you really want to adjust based on the average, right? Maybe the stat class, the midterm has 40%. We don't have midterm, right? Suppose midterm is 40%, right? And in other subject, principal, maybe midterm is 30%, right? The average is different, right? So how can you say one class has more spread than the other one? Just divide the mean. So the SD, the other mean, then that will be fair comparison, okay? Let me repeat the statement, okay? If you want to compare variance across different data sets, we're likely they have different mean, right? Depends on what you're measuring, right? You try to rescale your variance by dividing by the mean so that you can compare, right? Suppose I want to compare, is it students have more spread out in midterm and final exam, right? And we know that final carry more weightage than the midterm, right? Just remind you, we don't have midterm in this class, but anyway, suppose that's the case, right? And by construction, by definition, you expect final have higher mean than the midterm because more question in the final, right? So if you want to say final has more variance, which usually you expect to be, right? And then you have to divide it by the mean. Is that clear why you want to do that? Because you want to compare different data sets with different mean, right? If the same mean, it's fine. But usually with different mean, then you want to compare. Is that okay? Is that clear? Any question? So basically, you learn all the 5 different measures of dispersion, okay? And later we'll run Excel on this one, right? So mean is 3. We have shown this is the population variance. This is sample variance is 2.5, right? So how can you calculate population standard deviation? Just take square root of 2, right? And take square root of 2.5, you get the 2 answer. Okay. And CV just divided by the mean. okay, and times 100, right? And this is how you calculate this. Is that clear how you do it? Okay, of course, I don't compare, but imagine I give you two data sets and two different mean, and you can tell me which one is larger with the other, right? But I just don't do that because you know how to do it. Is that okay? Is there a question? Because we're done with the dispersion. Okay, we know mean, median, mode. Now we have 5 measures: range, interquartile range, standard deviation, variance, standard deviation, and coefficient of variation. Okay, we have 5 different measures. Of course, the last 3 is very similar, but anyway. But you know, there's the center thing you see, you know, most of the report you read them. Is there a question? If no, then we'll go to the last 2 shapes. Okay, the idea of shapes. And this is, I don't think you would learn it in your high school because it's something new. Okay. And there's a lot of things you can go about for this too. Okay. Here, we just try to give you the measure, some scratch the surface of what they are. And it's just trying to, why we have this is trying to say, if they tell us something abnormal, we need more advanced technique. Okay. It's a warning signal. Okay. If they are not belong to a proper range, then you should be very careful what analysis we can do. Okay. And we cannot teach you how to do those cases. Okay. But we tell you that you will learn in advance. Okay. Just telling you that, I mean, you look at the data, if within the normal range for these 2 measures, then you're fine. The first measure is skewness. It's asking whether data is skewed one side or the other. Okay. And for example, income is highly skewed, right? Because there's a few people earning so much money than the rest of the people, right? It's so far ahead. Okay, it's skewed. Right? And an exam is also sometimes skewed. Is like most of people can get a lot of mark, but then maybe usually 1 or 2 people don't come to the class, don't do the assignment, do nothing, don't attend the class, whatever. I don't know why, but they just get 0 for everything, right? But that's compared to the average, it's like 60, 70, 80, right? So that would be also skewed in that dimension. Okay. That how can we measure that, right? It's called skewness. We will talk about that. Later you will see it's very similar to the variance idea. Okay. And kurtosis is asking how extreme are the extreme values are. Okay. Values asking how spread they are, but it didn't tell exactly how extreme the extreme values are. And if the value are very extreme, then the usual analysis we are using then doesn't apply very well. So you will require a much more difficult technique. Same for skewness. If the data is very skewed, then the usual technique we apply will not work very well because usually you assume the data is fairly symmetric. Okay. Need not be perfect symmetric, but not too unsymmetric is fine. Okay. So that's the reason why this is, we just give you the idea how to measure them, and if they don't go crazy, then you should be fine. Usually the data is not do not go crazy for these 2, but so don't worry too much, but we need to talk about those. Okay. So the skewness is somewhat very simple. The formula looks crazy, but we look at the numerator first. I think the numerator one would be the easiest to see. Okay. The numerator one, in fact, if you still recall, variance is actually changed its square. Right? So now we change to 3. What does that mean? Remember, with the 3 times means that it can be negative, can be positive, right? Negative remain negative. Positive remain positive. Right? So if it's positive, right? that means that there are a lot of, there's some data is so big, right? Like the income data, right? If you add Bill Gates or Lee Ka-shing in the income data, right? He make more than hundreds of thousands of us, right? So that's why the data will be right skewed, right? And it will become positive, right? That's what you call positive skew, right? Otherwise called left skew, okay? And the only thing that you will see is the denominator, okay? This is the standard deviation raised to the power 3, okay? And you ask why we do that, okay? Idea is very simple, same as coefficient of variation. In this way, there's no unit issue, okay? And probably some of you may ask, okay, why don't we divide the mean to the power 3? That's fine. That's also fine. I mean, there's another measure. And there are many measures for skewness. This is one of them. The reason why I do that is because this is what you see in Excel, okay? Excel gives you this number. So I give you this number as well, right? So this is the Excel they give you. I think this in Excel that's called skew P. We'll talk about that later, but this is the skew P, skew population. So this is the answer, okay? And if you write down what is the variance, it's like this guy, right? So the SD is like this guy, right? This green thing is a SD. So this is the formula. Okay. And if the data is exactly symmetric, right? The numerator will be 0, right? Because the left-hand side, the right-hand side, this is the same. You take the power 3, they cancel out. So that's why it's symmetric, then there's 0. If right skew is positive, it's left skew is negative. Okay. So it means that as long as it's not too much different from 0, your data is not nice, you don't have to worry about it. If it's very positive, very negative, then you have to worry about your data. But of course, in our class, we just report this thing and that's it. We use the same tools. But in reality, you have to use different tools, as I told you, right? But in our class, we do elementary things, so that's it. You just know it and just say it and that's it. Okay, for our purpose. Okay. But do remind yourself that if too different from 0, your analysis have to be very careful. Okay. So there's a skew. And remember, you don't have to worry about the calculation, right? Because this is the Excel give you the answer. Right? You don't have to actually work it out. Right? So I want to draw your attention to this one. Okay. So here is if you calculate the skew function, okay, there's called sample counterpart. It's like this. You have to multiply this guy. Okay. So you ask what I'm doing this crazy slides here. Okay. One is because if you go to Excel, you do the skew. This is what they give you. Right? You probably ask why we do this crazy square root and crazy thing, right? Again, one reason is same as what we do the variance thing. Okay. If you try to calculate skew from the data, you have to adjust for the small sample problem. Okay, so that is you multiply this crazy thing. Okay, but don't worry, as I said, Excel, the skew, this exactly they give you. I give the formula, it's black because this, if you want to understand what's going on, it's like this. And why this formula makes sense, we don't explain, but you understand the logic behind when you go to topic 5. Okay, but just saying that if you actually ever use it, Excel is the skew function. This is the one you use. Okay. And again, if the data is large, right, it shouldn't be a difference, right? N and n minus 1, the similar, x squared the same n over n minus 2, right? So it's just same idea, right? This is bigger than 1, right? Right. So just idea, just adjust because you do a small sample, the skewness you measure is like underestimate, right? Because you just get the small stuff, right? You have to estimate how skew the big picture. So that's why you have to adjust it bigger. Same idea as a variant. But as I said, just take it as face value. You understand why we do it when we go to the middle of the semester. Okay? And just to remind you, this is the function called skew in Excel. Skew P is in the Excel. So just to make sure that you understand why we look at the formulas, is because when you try to look at your software, the software actually gives you something. You have to look at what exactly it gives you, right? Because here I give you this Excel function. I remember out you have to do some package to give you different measures. Just like the IQR depends on there are many versions. So make sure that you know what you're doing, right? Because the software owns a black box. You have to know which control to use because usually there are too many versions of things you can do. You never know what you're doing because our class focuses on Excel, so this is Excel. If you use other software like whatever software you're using, make sure that you look at the menu, check out which thing they give you. Okay. Otherwise, you don't know what you're doing, right? So here is the example how you can construct skewness from data. It's very simple, right? So same data set, right? This is the number, right? And then the second column, you calculate the mean, right? And then the third column is just subtract each data from the mean, right? 1 minus 3 is -2. 2 minus 3, -1, so on and so forth. And take a square root, square it. You saw the color, right? You take square for it, right? Square, right? All of them are positive. And you also have the last column is raised to the power 3, okay? And easily you can see this is symmetric, right? Because the mean is 3, right? And that's why the skew is 0, right? Is that clear? Because that will be 0, right? That's the numerator of the skew. And the sample one is just some adjustment, right? The same thing. Is that clear what we're doing? I'm not going to one by one why this is true, but I think you can check. Okay? Is that okay? If you have a question, then just ask me after the class or email me, but I guess you can read them without any issue. Okay? Okay, just make sure this is as is used here, right? Okay. Any question? Any question? If no, I assume this is okay, but you will rarely actually have to calculate this, okay? You will just use computer, okay? Just a graph, right? If a single model graph, a histogram like this, right? Or the frequency polygon, right? That is what you see, right? If there's complete symmetric is 0. Okay. And this is the one that is, you can see this one is like from 5 become 10, right? So you can see the mean, right? It's like 5 is 20, right? 20 over 5 is 4, right? The mean is 4. So it's 10 is much bigger, right? And you can easily calculate, right? But the same logic, this guy is super big, right? Add them up. Okay. You can see the skew is 1 point something, right? And the sample one is 1.6. Okay. And probably you want to ask how big you have a problem. There's no hard and fast rule. But if you think that is some people would be worried if your data, the skewness is more than 2, you'll be worried about that. But there's no particular rule why you want to worry. But if near 0, then it's good. Okay. And because whether you want to worry depends on what's the knowledge about what's the theory behind, right? If you think the data is very skewed, you find this data, then fit the skewness of the what you think, that's fine, right? But suppose you try to get the income data, you know it's skewed, but you have the symmetric one, then you have a problem, right? So depends on the context where the prior knowledge we have, right? And of course, if this is big, super big, then you have to worry about whether the usual technique we impose apply or not. But that would be you calculate the skewness, okay, based on the formula, okay. I'm not going to one by one how to plug in the number, but I hope you can able to follow it. I mean, if you want to understand the logic, you should try to do it by yourself, see which number plug in what, okay, because these are just plugging in the number here, right? You calculate standard deviation just using this formula, right? Plug in this number, and this I plug in this formula here. Okay, you're going to try to see at home. If you're still confused, just ask me. You should be able to do that. Okay. So this is positively skewed, right? That means the mean is higher than median. Okay. Okay. Do note that this is only true when the data is like single mode. Okay. If not single mode, this mean and median need not hold true. But in general, if skew data, mean is bigger than mean is bigger than median. Okay. I mean, this is generally true. Okay. Need not be need not hold in all the cases. Okay. But usually when you say the data is positively skewed, okay, then mean is bigger than median. Right? Same as the income data, right? Look at income data. It always the average income of the society is higher than the median. Okay. So if negatively skewed, right, median bigger than mean. Okay. This is what usually I get at the end of the semester, right? There are a lot of people getting very high grade. Median is somewhere here, mean is here, and some people actually don't attend class, whatever reason they drop out, whatever, they're very low. But most of you are doing very well, right? You are from the B school, right? One of the elite faculty in CHK, right? CHK is one of the elite school in Hong Kong, so you should be fine. Should be not an issue. Okay. Median smaller than mean. Generally, when you take negative skew, mean is less than the median, right? And the positive skew, median less than mean. Or if you have two modes, this is single mode. If you something like that, then this need not hold. But if the thing like this, usually in the data, usually they're single mode, that shouldn't be an issue. Okay. But in some market, it need not be single mode, right? Look at, say, the property market, right? So you have a regular housing, right? And you have some very expensive bungalow, right? Small house, independent housing, then that one is like another mode there. Look at the pricing data, right? So some houses like with less than $10 million, and some house like $100 million, right? That's a double spread. But I mean, in general, it just right in this one, okay? But you can take this as a normal thing, right? I mean, most skill usually you mean bigger than median, but not always, but in general, yes. Right. So probably you again wonder why we care about skewness, right? As I said, right, because skewness actually overlooked in a lot of calculation, and that is a problem. Okay. And financial crisis is basically people don't look at the skewness, and it is a problem there, right? And doing lottery is also the same. Okay. And last one probably you would care most is because of people would buy stock willing to give premium to highly skewed stocks, right? It's like lottery ticket, right? You want to pay a lot for, say, Tesla, Google, Apple before they go break. You pay a lot for the startup because you think one of them can become great in one day, right? And you want to pay for that. And if the stock is like more likely to be skewed, then you actually pay more premium to that. And the finance theory, these days actually trying to develop model, take skewness into account. And there's a skewness premium in the recent theoretical model, because in empirical, we figure out that people pay extra for the skewness, because if you learn finance, right, you know there's a mean variance approach, right? We pay for the financial assets that have high mean return, and we don't like assets that have a high variance, right? And then we talk about skewness. And now recent data shows us we actually pay for the skewness. So not just mean variance, now we have skewness. Okay, so that's why skewness is important. Lastly, we want to look at kurtosis. It's also the same. And if you careful enough, or you would notice there's nothing new here. It just changed from 3 to 4. Okay, there's nothing new there. So that means that this is positive. Okay, it's always positive. Okay, and the same reason we divide it into we divide the sample standard deviation. Okay, and Excel don't give you this directly. Okay? There's no the Excel function they call KURT, KURT. Later you will learn. It's not this result, but rather they'll give you the sample counterpart, which is this guy. This crazy thing. Okay, I'm sure that you don't want to look at it, but that's a formula. If you want to calculate from scratch, the formula. This is the formula that, I mean, it is sure that's crazy. It is this guy. Okay, and it is it's not just the kurtosis -3. So I want to mention why we need to have a -3 here. So let me define this one. So we usually don't care about the kurtosis by itself. What we care is called excess kurtosis. Okay, and why we care about excess kurtosis instead of kurtosis? The reason is being that we want to compare to what we call the bell shape, the normal distribution. Okay, and then we'll tell you why we care about the bell shape, because at the 6th topic, we will mention what we call the central limit theorem, which essentially said if what you observe is average outcome of many different things, then it's a normal. Okay, the idea is like IQ, for example, is a normal, it's a bell shape, because your IQ is determined by your genes, what you eat, what temperature there, where you have gone, where you have what you have learned, so on and so forth, right? Because there's a lot of depends on your DNA or the chromosome. Forget about forget. I mean, just forgive me my biology, but I mean, there's a different acid, right? That's combined, how you combine. So it's a lot of random thing. When a lot of random thing add together, there's a bell shape. There's a central limit theorem. Later we'll talk about. And IQ, the height, right? The height also depend on what you eat, right? Every day, right? The temperature, so on and so forth, right? And that means that it's a very natural that bell curve is something you observe most of the time, right? So that's why exams, you have a bell curve, okay? Normal. But when you go to CHK, it's not just bell curve, because we already select the top of top here, right? So that's why the bell curve doesn't apply very well, right? But anyway, that's the reason why we care about excess kurtosis, is because a bell curve is 3, okay? So that's why you want to see if more than a bell or less than a bell, okay? If your excess kurtosis is 0 or close to 0, you don't really worry about it, okay? In the Greek, I think Greek or Roman, I forgot, it's going to be Socratic. And if more than that, right, you have much fatter tail, okay? If lower than that, you have a lower tail, okay? And I want to remind you that because most of our analysis is based on the bell curve idea, which you will see at the second half of our course. So where if your data actually a problem of this kind of fat tail and issue or fin tail issue, then our analysis doesn't apply very well. You need to be very careful. Okay. But anyway, but that is the idea. So this measure in the Excel is KURT, KURT bracket. That is the answer. Okay. So you would just use Excel to calculate the answer. Okay. And the bell curve is the blue one. Okay. The red one is the fat tail because much fatter. This is the one that the excess kurtosis is more than 0. Okay. If you have the brown one, the excess kurtosis is negative. Okay. Just whether 0 is the boundary. Okay. And just to remind you that because so complicated, Excel will give you the answer automatically. Okay. But you probably ask, okay, this is so complicated. Again, I explain why, because this is the better estimate. And you will, but this is trying to asking this in the population. Okay. We're asking this in the big picture, but when you have data, you use that one. Okay. Is that clear what we're doing? Okay. Give you an example. I'm pretty sure that you will be bored by the math, but I try to, because this one is much more complicated. I just go one by one because make sure that you understand what's going on. Okay. So I'm pretty sure that you will not have problem to understand this is data, this is the mean, this is minus mean, this is square, and take to the power 4. I mean, that is not a problem. Okay. So the only thing is look at the population kurtosis, right? Population kurtosis is add them all up divided by n, right, at the numerator, right? This is 34 is this guy. This 5 is n, right? And this guy come from here, right? Because it's summing up all the square distance and divided by how many of them. This is also n again. Okay. Is that clear how you get these numbers? Right? So you subtract 3, that is excess kurtosis. Okay. It's negative. So it means that this is thin tail, right? Much thinner. There's no fat tail. It's much thinner. Is that clear what this data is? Right? Is that okay? Now, the next is exact kurtosis, which you can find if you put this number 1, 2, 3, 4, 5 in Excel, then you cut this, you're done, right? But probably you want to see how we calculate that from scratch. Okay. The idea is the following. Okay. 34, this is green color, right? 34 come from here. It's here, right? And how you get 2.5 here? 2.5 actually come from the sample SD. Okay. This is 10 is from here, right? You divide it by 4 is 2.5. So 2.5 is here. Okay. And the rest will be just, this is n, right? This is n plus 1, n minus 1, n minus 2, n minus 3. Right? And this is n minus 2. This is n minus 3. Right? And while we are 4 there, let me check. Oh, this is n minus 1, right? So you can see I can't remember the formula. So you don't have to remember the formula anyway. Okay? Is that clear why we have this formula? Everything is just come from the formula. Nothing special there. Is there any question? Any question? So don't worry, you will be actually, when you work, you actually have the formula that apply. Okay? You don't really work it out, but I have to show you this formula exactly is the formula that we're using. And you can check that Excel gives you this answer. Okay? So the question. Any question? Okay, I erase it. So for the last 5 minutes, or 3 minutes, maybe I shouldn't continue, but I just finished this example, and we're done. Okay. So you can see this example. It's the same thing, right? We want to calculate kurtosis, right? So the idea is very simple. Just go again. How you get this number? Okay. So this number is here, right? You divide it by n, okay? And this number is here, right? And this is n as well. So this is the calculation of the kurtosis, right? And the population of kurtosis is very small, right? You would not be worried too much about it, right? But when you look at the sample one, before I go to each one, that's very big, right? So that's why we have to use the sample one. We never use the population. Population one is not very good. Okay. And then we go one by one again to this, go to here, right? Okay. And the S go to here. Okay. And the rest is just n, right? This n plus 1, n plus 2. Sorry, this is n. This is n plus 1, n minus 1, n minus 2, n minus 3, right? This is n minus 2, n minus 3, right? And 4 squared is just n minus 1, right? So this formula, okay. I hope convince you that this is the formula. It's not complicated, right? Just plug in the data, okay? And we'll talk about the last two measures in the next class, and then we'll Excel. So next class, make sure that you bring your computer, Excel. We will talk about Excel. If you don't, I mean, your friend will have, it's also fine. Or if you forget to bring it, doesn't really matter. You just look at the video at home and then try to look at the Excel. Okay. So I will see you next week. This Wednesday. Okay. This Thursday. This Thursday. Yeah, I'll see you this Thursday.